So, welcome to the second part of your nuclear notes. This one is going to cover a variety of topics, so we're going to try to move through it as quickly as possible. So, this first part is talking about the effects of radiation, and the effects actually depend on the amount of radiation exposure and how long. Massive doses can actually be deadly. Our DNA is very sensitive to alpha, beta, positron, and gamma, and of course X-rays. That's why whenever you go to the doctor to get an x-ray, if you're a female, they always ask you if there's any chance you can be pregnant, because x-rays can be detrimental to a growing fetus. Also, gamma rays are remember we talked about that, they are the most penetrating and the most harmful. So on this slide, I've underlined what needs to go in the blanks on your notes, and I'm just going to let you pause this and copy that down real quick, because I'm going to talk about those three things a little bit further on the next slides. And then, of course, the definition for the REM is also, or REMs, are also on the next page. So I'm going to give you a chance to copy this down, and then go to the next slide, pause it, and copy that definition down. So go ahead and pause this video and copy this definition down of REMs. Remember, REMs are what we measure radiation exposure to, and it is called a Roentgen, which is a unit that measures radioactivity. So we're going to go through these next couple of slides pretty quick. A film badge is worn by a person who's working with radiation. Oftentimes you'll see people in hospitals wearing them, and it's literally a piece of film, and that when it's exposed to radiation, the film darkens, and about once a month or so, they send the film out to see how much exposure has been had by the employee. A Geiger Muller counter is a gas-filled metal tube used to detect radiation. There's one picture of it. Here's another picture of a Geiger counter. And when you see movies and you see them, detecting radiation or whatever, and you hear that click, 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 and it gets faster and faster the more radiation, that's exactly what this is. And that's because radiation produces ions, and ions conduct a current that is detected by that instrument. A scintillation counter is a device that uses phosphorus-coated surface to detect radiation. They're not used as often. The applications of nuclear radiation, again, I'm going to pause this and let you, or you pause it, write down these things, and I'll talk about them in the next few slides. The 2 and 3 kind of go together, and you can just write down tracers for that. Again, just write down tracers for that second blank. So radiocarbon dating, that is how they figure out the ages of something. That's why when they find a fossil, they say, oh, this fossil was 14 million years old, and that's because of everything that has ever lived has carbon-14 in it, which is an isotope of carbon. Remember, we said there's carbon-12 and carbon-14, and based on how much carbon-14 is left in the sample, they can back calculate and figure out roughly within a margin of error. Sometimes it's a big margin of error, sometimes it's not. They can figure out how much or how old the fossil was. Radioactive tracers, there's two types. There's medical, and then there's also agriculture. And what they do is they tag something with a radioactive isotope, and they pass that along, or they follow it through. In the case of medical, they might follow it through the digestive tract or something like that. So, and the last thing I want to mention about this is radiation therapy, which is, of course, used to treat cancer. When you have, when you talk about chemo and radiation, it literally is radiation that they are treating the cancer cells with, and they target it specifically to get the area that the tumor might have been in. But you got to remember that some healthy cells are killed as well, so you got to weigh the benefits and the risks together. It's gamma and beta particles are the two that are most commonly used to treat cancer. So half-life is a term that you need to be familiar with. It is the time required for half of an atom to decay. All things that are radioactive have a half-life, and all things that are radioactive will spontaneously decay. It just happens on its own. We talked about carbon-14 earlier when we were talking about carbon dating. So we need to know how to calculate a half-life, And literally it's dividing by 2, so it's really easy. On your notes, I forgot to leave the little T-chart on there, so if you'll draw that little T-chart in there, yours is easier to draw than mine, and it takes you through how to work this half-life problem. So here I have this problem that says phosphorus 32 has a half-life of 14.3 days, and it wants to know how many milligrams of phosphorus remain after 57.2 days if you start with 4 milligrams. So the best thing to do is make you a T-chart and do amount on one side, time elapsed on the other. And then you put your starting amount, which we said was 4 milligrams, and that's at time 0. Okay? So then what we'll do is we're going to double our days until we get to 57.2 days. So here we go. This is one half-life, and then 14 to 28 is the second half-life. 28 to 42 is the third half-life, and then 42 to 57 is the fourth half-life. So we've gotten to the amount of days. So now we'll go over here, and remember it's half, so we're going to divide by 2. 4 to 2 for the first half-life, 2 to 1 for the second half-life, 1 to 0.5 for the third, and then for the fourth it's 0.5 to 0.25. So after that amount of time, what would be left would be the 0.25 milligrams. So that would be our answer. On your left side, you have 2 problems to go through, but since this is a flipped lesson and I'm not here to answer questions, I'm going to work those problems with you. So what I would like you to do is try the chart on both of them and then check to see if you did it correctly. This little slide is just a different way you can work it. You could figure out how many half-lives were and then just divide by 2. But honestly, if you will use the chart, it's much easier and you won't mess it up as much. Alright, so here is the one that I want you to pause the video and try to work it yourself with that little T-chart. And then restart the video and see if you did it correctly. So, how'd you do with that? Hopefully your chart looks something like this, and you see that at the end of 415.2 days, you would be left with 0.25 milligrams. Now, the next example is going to give you the amount you started with and ended with, and it's going to want to know how much time is left. You can use the same setup, so let's look at that. Alright, so I need to make a couple of changes on here because I know the one in your notes is a little bit differently. First change I made was on the days. Cross out that 0.24 and just use 3.8 days because the 24 part on the end is a little tedious. And then I had a different question in my PowerPoint than you do on your notes, so use the one that's in your notes. So pause the video and work that out. Again, you can do it the same way, except this time you're going to decay the amount and then match the days to it. Alright, so let's go ahead and do this one together. We started with 100 milligrams. We divide that by 2 and we get 50 milligrams. Half is 25 milligrams. Then we have 12.5 milligrams. And then we get to the 6.25 milligrams is what they asked us to do. Okay, so if we look at that, we see that we went through 1, 2, 3, 4 half-lives. Okay, so remember, at 100 milligrams, that's times 0. So when it goes through 1 half-life, it would be 3.8 days. When it goes through 2 half-lives, it would be 7.6 days. The third would be 11.4 days. And then finally, which is going to be our answer, would be 15.2 days, is how long it would take for this sample to go from 100 milligrams to 6.25 milligrams left. So the last part of this lesson is going to discuss the difference between fission and fusion and give you some examples of each kind. So let's start with fission. Nuclear fission is the splitting of atoms, or a splitting of nucleus into smaller fragments. So what you're going to start out with is you're going to start out with a heavier nucleus, and you're going to end with something that is smaller. So that's how you'll recognize if it was fission, because it's splitting it. It's caused by the bombarding of the nucleus with neutrons, and what happens is it actually, the neutrons cause it to split and produces more neutrons. Then those neutrons go and now they bombard an additional nucleus. So it actually creates what's called a chain reaction, which is your blank. And again, this is an enormous amount of energy that it releases. 1 gram of uranium, it produces the same amount of energy as 3 tons of coal would. So it's very, very powerful. When we talk about nuclear plants or nuclear energy, we are talking about a controlled fission reaction. And a controlled fission reaction uses things to control those neutrons being produced so that you don't produce too much. So this is just a picture of the what a fission reaction looks like. We have the neutron right here, and it's bombarding this nucleus, and it splits, and when it does, it produces more more neutrons, which go and now bombard other nucleus, and then this one. And so you can see that if it's not controlled, it could get out of control really, really quickly. And then what happens when you're talking about nuclear plants is you have the nuclear meltdowns. I'm sure you remember in the news a couple years ago when the tsunami hit Japan, the nuclear reactor had a meltdown because of the loss of power and the loss of being able to control that reaction. That's what happened. So when we're talking about nuclear power plants, of course, it's using nuclear reactors to produce heat, which then is converted to electrical energy, which then we can use in our homes. There are 5 main components of a nuclear reactor. The first one is shielding, which is the radiation absorbing material. The second one is the fuel, and of course it's most often uranium. The control rods are very important because what the control rods do is they absorb some of those neutrons we just talked about so that we're not producing so many neutrons, which then are bombarding other nucleuses. So they're very, very important. The moderator, which is mostly water, sometimes it can be carbon, is used to slow down those neutrons that are produced in the chain reaction. So first of all, we have a control rod absorbing them, and then we have a moderator slowing them down. And then the last one is the coolant, and almost always it's water, and it acts as the coolant, but it also transfers the heat between the reaction and the steam turbines, and then the steam turbines are actually what's going to be producing the electric current, okay? So the good thing about nuclear power plants is they produce a great amount of energy with actually very little. It's very clean energy, but they do produce some radioactive waste that we'll talk about here in a second. Here's a visual of what that kind of looks like, the way it works. You have the control rods here, and then you've got the steam generator, and it's absorbing the heat, and then it turns the steam turbines, and then produces electricity, and then it goes to our homes. So another example of a fission reaction is the atomic bomb, which I know you're all familiar with, that was dropped during World War II, and then that's going to bring us to fusion in the next slide. Okay, so nuclear fusion is kind of the opposite of fission. In fusion, you're taking light nuclei and combining them to form a heavy, more stable nuclei. They actually, fusion reactions produce a lot more energy. 1 gram of uranium is the equivalent of 20 tons of coal, whereas the other one was 1 to 3. The sun and the stars are an example of a fusion reaction. What's happening there is 4 hydrogen nuclei combine at extremely high temperatures and pressures, and they actually are forming a heavier, more stable helium nucleus. The hydrogen bomb was an example of an uncontrolled fusion reaction, and a hydrogen bomb was different than the atomic bomb. And then the third thing that they're trying to figure out is trying to use fusion as a source of energy, because it produces so much more energy, and then their byproducts are much less harmful than fission reactions. Research is being done. I personally think you'll see that in your lifetime, maybe not in mine, but I feel like you might see that in your lifetime, a fusion reactor. But the problem is you need a really high temperatures, and most of the material that we can produce right now can't withstand the high temperatures. So the last thing we need to talk about is nuclear waste, and that is nuclear waste produced from fission and fusion reactions.
The waste produced from fission reaction is a lot more, or can be a lot more harmful because it's radioactive, but the types of nuclear waste are the spent fuel rods, and that's the one that contains the uranium. When we dismantle nuclear power plants, the military, and then of course the radioisotopes that are used in many hospitals. So those are some of the things that the scientists are trying to deal with. How do we deal with that? Because it is radioactive once it's started decaying, but it stays radioactive for many, many years. So right now, the type of containment that we use is either on-site storage or off-site disposal. Remember that every radioactive substance has a half-life. For some, it's only a few months. Others, it can be hundreds of thousands of years. And so the on-site storage is the most common for spent fuel rods. Also, there can be water pools, because if they store it underwater, the water absorbs some of that. And then the dry cask, which are going to be concrete or steel that are buried. There are currently 77 off-site disposal sites in the United States. It could be more than that. I'm not sure how old that data is. But the newest site was in Las Vegas in the mountains. So that is going to end where we're talking about nuclear chemistry. So stay tuned on the next slide for your jokes. Okay, time for jokes. This time we have a theme, and it is space and planets and stars. So let's start with the first one. How do you organize a space party? You plan it. What do you get when you cross Santa Claus with a spaceship? A UF ho 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 ho. What kind of songs do the planets sing? They sing Neptunes. All right, see you in class.